Okay, what I want to talk about now is the concept of factor of safety, or really, maybe before I talk about factor of safety, this notion of design. Okay. Now, when we did this problem, this is not really a design problem. Okay. Forces are given to you, and all the geometry is given. You can go from there and determine stresses in the component. Right? That's sort of a forward process, right? Everything's known. You go through, do the analysis, and then that gives you the stress. And so it's, you might call it an analysis type of problem. A lot of times as engineers, or actually arguably most of the times as engineers, we're designing the component, so we don't know the dimensions. The question is, how big does this part have to be so it doesn't fail? So this is now a design problem. So let's say you knew all these geometries except maybe you didn't know how thick that this plate needed to be. Like maybe you didn't know this quarter inch, right? The other geometries maybe are fixed for some other constraints of design. So then the question is, how thick does this plate have to be so that the part is not thick? Okay? So that would be a design problem. So in that situation, you don't know the area, right? You can figure out the forces, but you don't know the area. You don't know the thickness. That's what you need to find. Now, what about the stress? Well, this is where the notion of factor safety comes in. So if you're doing a design problem, okay, you can determine the normal forces, you do not know the geometry, that's the design part of it, but we have to design it to meet some condition on the strength. So we're saying that the geometry of the part has to be, you ought to figure out the size of the part, in this case, the thickness of the plate, such that the stress doesn't exceed some acceptable value, some allowable value. Right? Now, if you think about it, the obvious number you want to look at is what is the stress at which this material fails. Okay? So that value is what we refer to as the failure strength of the material. So we want summarize this. So this is our equation. Want find A, right? We know N. Get that from sum of forces, sum of moments, right? And what do we use for this condition? Well, what we're basically saying is the stress has to be less than some allowable stress. Okay? Stress has to actually be less than some allowable stress. What we're trying to do is N over A has to be less than some allowable stress. Right. So from this, we can then less than or equal to. So the limiting case is when area, when this, the limiting case is when this inequality becomes equality. In other words, the area is equal to the, well, let's do it this way. So if we solve for the area, divide by sigma allowable multiplied by A, you get that the allowable stress has to be greater than or equal to normal force divided by this allowable. I think this, let me just pause here and mention that. This is an important thing to consider. It's always good to have in your head a feel of which way design should go. And I think this is pretty obvious, and it's easy to but obviously, as the cross-sectional area in this particular scenario gets bigger, part can withstand more force, right? It's stronger. I think that's kind of obvious. But you can see it's borne out through this. So the area has to be bigger than or equal to the internal reaction force over this allowable. The limiting case is going to be when this goes to equality. Well, we can use that to get that You can use this to determine the area, or in this particular way, like the way it poses the same problem. We know the area, we know this is 3 inches. Okay. Now what is this allowable stress? One obvious thing would be the failure strength of the material. When does the material fail? This is what we call now, you can actually test that with a sample material and potential test specimen and figure out at what stress the material fails. The problem with that is if we design the area to be that, then you're right at the point where it's going to fail. So for one reason or another, the operating force might go up more than what you think it does. It will fail. Or maybe you have some material with a flaw, something else that actually makes the actual stress at which it fails a little lower than what you tested it at. Again, it fails. So you've designed this part with no margin. That's not what we like to do. We like to have a little margin of safety. In engineering, we call that margin of safety the factor of safety. So instead of using the failure strength, we use the allowable strength as equal to failure strength divided by some number, some factor of safety. Okay? So this factor of safety is greater than, well, in some cases it's equal to 1. It's always got to be, typically it's greater than 1. Typical values are like 1.5, 5, even upwards as much as 4. Okay? So this means the allowable stress is less than the failure stress. So you're actually designed to a lower allowable stress than the failure stress. So that is the margin you have, the difference between the allowable stress and the actual failure stress. Nobody can like it. The failure stress is the allowable. Oops, I'm sorry. Failure over the allowable stress. Okay? Actually, honestly, I use it this way. But the way it's used more often is this way. Okay? Obviously, sometimes what students will forget is the allowable here is the failure. You can memorize the equation. I think it's kind of silly. I think this is one of those great examples where it's not an equation you want to memorize, but it's a concept. Failure, the factor of safety, right, is a number that's always greater than 1. It's how much margin you basically have. So if the factor of safety is greater than 1, then the allowable stress, obviously has to be less than the failure stress. So that tells you that failure stress divided by the factor of safety is allowable. Not something else like the failure stress times, not the factor of safety times the failure stress. That way the allowable stress would be greater than the failure stress. And obviously that makes no sense. The negative margin, right? You're doomed, right? The airplane is going to crash. Okay? All right, so that's the notion of factor of safety. So let's go back and revisit this problem and just do a real quick example. These concepts are kind of subtle. Well, they're simple, but they're also very important. And I think it does bear some time. Again, this is one of those cases I want to pause. Don't just memorize this equation. Don't just memorize divide by failure by factor of safety that's allowable for this equation. Think about the concept that's going on. What factor of safety is. It's not that hard. We're not talking about quantum mechanics, but this notion of developing a design sense or engineering intuition is really, I think, a strong skill to have. Everybody should always be trying to develop this. A better engineer. All right, so let's do this as an example. Let's look at this case. Let's say we don't know what this thickness is. Let's find the thickness. Right, we have to design the appropriate thickness. Let's say that we're using material, some sort of plastic material, where the normal failure stress 300 psi. We want a factor of safety, in this case, of 3. We want to be really conservative. Okay? So if the failure strength is 300 psi, the factor of safety is 3. That means we have to design this to an allowable stress of only 100 psi. Right? The failure stress is divided by the factor of safety. This is what we're designing to. Right? It's another way to think of it as we're considering allowing the material less strength. Right? Excuse me. All right, so if that's the stress we're designing to, we have this, it's the same geometry up here, so the normal force is still 100 pounds, or minus 100 pounds. All right? So, the normal force is minus 100 pounds. So this is compression. Now, most materials, unless it's stated otherwise, when you have a failure strength, let's assume this is the same in compression and tension. And sometimes we have different compressional strengths. Let's assume it's the same. All right. So we need to figure this out to some extent. Normal force over the cross-sectional area needs to be less than or equal to this allowable stress, right? That's our design equation. Right? And we need to find A. We know that A, in this particular case, is going to be the thickness times 3 inches, right? That is that cross-section. Okay. Now, let's just talk about the sign. So obviously, if I put the negative in here, this becomes a negative number. So you really want to look at the absolute value. I think this is kind of obvious. I don't want to get too much math of it, right? But obviously, this case, we're looking at the absolute value, right? But even goes to the negative value. It's that if you did it without considering the absolute value, then you would keep increasing the compressible load to infinity. And you're always going to be less than your negative number, right? So it's really the absolute value. Okay. All right. So let's find the area. In the limiting case, the area has to be greater than or equal to this force, it's 100 pounds, divided by the allowable stress, which is 100 pounds per square inch. The pounds cancel out, so this is equal to 1 inch squared. That's the cross-sectional area. So the area has to be greater than or equal to 1 inch squared. 2 inches, 3 inches, whatever. But the limiting case is the area 1 inch squared. Right? Now, if that's the situation, use that here. We want T times 3 inches. We want that to equal 1 inch squared. That's the limiting case. So that tells me that T has to equal 0.3 inches. That's the thickness. Okay? So that's the minimum thickness. Okay? It can be greater, but as soon as you drop that thickness lower than 0.3, stress will go up, and exceed the allowable value. Right? Sometimes we're going to do design problems where the dimension gets smaller and the stress goes down. Okay? So it's not always that the more conservative estimate is when the value goes up. Okay? Now, another way you'll sometimes see this problem written is, plate thicknesses might come in standard stock sizes. So maybe the thicknesses come in 1/16 of an inch increments. So that means it comes in 1/16 is 5 inches, right? The next one's going to be 2/16, which is 8, which is also 8, 1, 2, 5, which is 16 is 0, 6, 2, 5, 16 inch. The next one would be 3/16 of an inch, which is 0.1875, and half of an inch, I'm sorry, quarter of an inch is 0.25, so on and so forth. The plate only comes in those thicknesses. So the design problem might be find the thickness of a plate to the nearest 16th of an inch. That'll give you a factor of safety of 3. Now in that situation, 1/3 is somewhere in between. What's the next one? Quarter. It's somewhere between 5/8. It's 5/8 of an inch. It's 6. Three-eighths is 0.375 inches. Okay, so that's on the high side. Plate below that, 5/16, right? And that's going to be 5/16, which would be 0.3125. Right? So this situation falls in between 5/8, sorry, 3/8 thick and 5/16 thick plate. Which one should you use? Well, obviously, you go to the thinner one, even though that actually is closer. The factor of safety is now less than 3. So you need to always, when you have these situations where they say find the nearest 16 or whatever, you have to go as a designer to the more conservative value. So in that situation, it's actually 3/8, right? So you want to use 3/8 plate, right? Because that will give you a factor of safety greater than 3. Right? Even though 0.333 is closer to 5/16, if you round it, you go to 5/16. 5/16 will give you a stress that's less. I mean, it'll give you a factor of safety less than 3. Right? So therefore, it would not meet this criteria. Right? So you have to go to the more conservative value. Sometimes that'll mean the dimension actually gets smaller. Maybe it's a hole. The more conservative value might be a smaller dimension. Sometimes it might be a bigger dimension. But you kind of figure that out, right? When we're talking about finding it, to the nearest quarter inch, whatever, you always want to go in the direction that makes it more conservative. Okay? All right. That's all I wanted to say about that. Thanks. One of these days I'll try to do a better explanation of factor safety. It's really a simple concept. It's simple to do. I don't know why. When we're curious about it, I tend not